So this video just contains two examples that use the small gap approximation. Alright, so this first example, it's a shaft being pushed through a sleeve. So this blue part is the sleeve. It actually goes all the way around, so this is kind of a cutaway of it. The shaft diameter is 6 centimeters. The sleeve inside diameter is 6.02 centimeters. So you can see, yeah, there is a pretty small gap. And the fluid that's in there is oil, which is viscous. And both of those things, small gap plus more viscous, means it's going to be a good approximation to use the small gap approximation, since the gap is small. So we're going to assume it's a small gap. Okay. What we're going to try to find is the force to push that shaft at a steady velocity, so it's not accelerating, of 0.4 meters per second. So let's call that U. All right. And just so we don't have to just immediately plug in numbers, let's make this length L, and we're given this length is 40 centimeters up here. And I'm going to want to use an R here, call it R1 instead of a diameter, just to make my life a little bit easier. All right, so what we want to do in these things, we're trying to find a force. So normally if you're trying to find a force or you're trying to find a moment, you want to write your stuff from statics. You want to start with a free body diagram, and you could have drawn it up here. It's kind of hard with the tightness of that shaft there with a small gap. So we have this force, that's what we're trying to find, and we know the sum of the forces equals 0. Okay, the other force that's acting on this is just the force due to that fluid friction. There's nothing else going on around this shaft. Now we're going to assume that there's just air or something on these ends, so we're going to neglect end effects. So the only thing that's going on here is we have a resisting shear force, tau omega times the area where that's acting. Okay, so if we say the sum of the forces are 0, we have just these two forces, and so they have to be equal to each other, equal and opposite. So F is going to be tau W times A, tau at the wall. Okay, our tau at the wall, mu du, and normally we would put in a du dy, right? Here we could draw this as being a y, but it's actually, with cylindrical coordinates, that's actually an r. Okay, so every time you're going out or towards us out of the page, you're going in the r direction. That's okay, it still works with cylindrical coordinates du dr as long as your velocity is only in that one direction. All right, times A then. So that was our tau wall, and then there's our times our area where it's acting. All right, so first thing, let's go ahead and magnify that gap. And if we do that, what we're going to see is we have the sleeve here, and it's stationary. Okay, and down here we have that shaft that's moving at U, big U, and this is our H. In between, what we have is small gap approximation is a linear velocity profile. It's supposed to be a straight line. Okay. So what we can do then is just say tau is mu du dr in this case, because this is in the r direction. Okay, but for small gap, that's going to be mu times u at the bottom minus u at the top, since 1 is 0, over h. Okay, we're not going to worry so much about the direction of this. We can figure from this picture how that's working out. All right, so our force then is just mu u over h times A. Okay, so let's think about the A. The A is the area where that shear stress is acting. Okay, so in this case, if you look at it, that shear stress is acting over that whole outside surface. Okay, so the outside surface is surface where shear acts. It's not the cross-sectional surface, so it's not pi r squared. It's the circumference times that length. So 2 pi r, so A is 2 pi r1, or pi d would have worked, times rl. Okay, that's the surface where the shear stress is acting. Okay, so putting this all together, F is going to be mu u over h times 2 pi r1 l. All right, and I can just plug in all my numbers. Be very careful with your centimeters to meters and so forth. I'm going to skip over that for time's sake. I'm going to get 793 newtons. Okay, and just so you can relate a little bit to that, that is about 180 pounds. Alright, it's a lot because that's oil in between, so it's really hard to push through that oil. If it was actually air, it would be easy to push it. Something less viscous, it'd be a lot easier to push that rod. Okay, so here is our force. The other thing we were going to look for was power, and power, you guessed it, it's Fu. That's going to be our 793 newtons times our 0.4 meters per second, which is going to give us 317 watts. Okay, so Newton meter is your energy. It's the same thing as a joule, and a joule per second is a watt. So that's how we get watts. Alright, so let's go on to example 2. So that was a linear motion. Example 2 is the same thing, only instead of pushing that rod through, what we're going to do is just turn that rod. Okay, and instead of finding the force required to push it, we're going to find the torque required to keep it spinning at a speed of, that's a capital omega. Okay. So again, let's call this R1. Okay, and when we find the torque and moment are essentially the same thing. So a lot of times what we're going to do is call this torque M for moment. All right, so this is a little bit different. Let's zoom in again. Let's zoom into this top here. Okay, and what we have is, here's our sleeve. Okay, and here is our rod, and if we're up here, the rod is moving that way. Okay, at some velocity u. Okay, here is our h, and our velocity profile. The sleeve is stationary. Still a small gap, so we're still going to get a linear velocity profile, kind of like that. Alright, so this is very similar to what we had when we were pushing it through. The difference really is going to be our velocity is different, and now we're talking about torque or moments instead of forces. So for a solid spinning object, this is something to remember. If you have something spinning, and it's going to change velocity as you go from the center out to an edge, and something really with a big diameter is going to have a high velocity out towards the edge, and it's a pretty simple equation to find that velocity. So to get that u, what we're going to say, that velocity at r is equal to omega times r for any particular spot along that shaft that's spinning. So this u here at the outer edge has to be omega times r1. Okay, and our torque equals our moment, which is going to be m, and it's going to equal F times r1. okay, because our tau here is going to act tau wall in that direction. So this spinning shaft, it's spinning through the fluid's going to pull back on that shaft in that circular omega or theta kind of direction. Alright, so what we want to do is not sum of the forces equals 0 in this case, but sum of the moments equals 0. Okay, so we have two moments going on. We have this applied torque and that has to counteract our shear stress. And our shear stress moment is going to be our force, total force due to that shear stress around that thing, times that distance, R1. Okay, and that's going to equal tau at the wall times A times R1. Okay, so for our small gap, because this is still a small gap, we're going to say our du dr equals u over h, and our u is omega r1 over h. Okay, so we can plug this all in, and our tau wall then is mu omega r1 over h, and so our moment, plugging everything in, is our tau mu omega r1 over h times our area. Now this shear stress is still acting over that same area, the outside surface of that rod, which is going to be 2 pi r1 L. Okay, and then we have to get a moment r1 here. Okay, so our moment is 2 pi omega mu L over h times r1 cubed. Alright, and our power now, remember power for something spinning, power is torque times omega. Okay, and so we just need to multiply that by this m times omega, and we're going to get a omega squared in there. So 2 pi omega squared mu L r1 cubed over h is our power. Alright, stop here and do quiz questions 3 and 4, please.